Okay, let's continue, please. Well, what we see here is a curve. What we see here is a curve telling us the relationship between temperature and time in the solidification process. Okay? As you see, up here we have got molten material at a temperature which is well above melting point, which is used in casting processes. That's the pouring temperature. Then, once we are putting it into the cavity, and cavity is filled in, the mold is filled in, it takes some time for the molten material to lower temperature to melting point first, and then it takes some time where there is no change of temperature, but there is a change of state from liquid to solid. And after that, once material is solidified, it takes some time for the material to cool down to room temperature. Okay? Does it make sense? This curve, however, this curve does apply only to pure metals and eutectic metals. How about other materials? For non-eutectic alloys, it changes slightly to this. In non-eutectic alloys, the way that it behaves is slightly different. Instead of having a horizontal line for the change of state from liquid to solid, we will have an angular line just like that. What explains this? What explains this? Who said that? Okay, say that louder a little bit.
The solidification of alloys.
The solidification process.
Yeah.
It is different from what we have for the pure metal. What's the difference? Instead of having a horizontal line for the change of state, it is on an angular line. What explains this? What explains this?
Components have a fragment.
Exactly. Look at this composition right here. 50% nickel, 50% copper is an example of an alloy which is non-eutectic. Okay? At this temperature, solidification begins. Within this region, we have got two-phase regions of solid and liquid at the same time, meaning that there are particles of solid floating in a liquid phase. And eventually, gradually, those grains of solid grow, and eventually, what we get is a single solid phase. So at some time, we will have liquid and solid phases present at the same time. So solidification begins at this temperature, which is a higher temperature, and is completed at this temperature, which is a lower temperature. It's not only melting point. We will have a range for melting. We don't have just a single point as melting point. Okay? And now we know why it happens and how it happens. Okay? Well, now let's take a look at the solidification process of a pure metal or a eutectic metal. Talking about pure metals, the way that they solidify is like this. Here you can see a cavity and the material which is solidified inside the cavity. The first point to solidify is the first point to solidify is the boundary or the surface of the part, because it does interact with the inside wall of the cavity or the mold. And then it's the first point which lowers the temperature to a point below melting point. As a consequence, a skin is produced on the surface of the part, as I explained before. And as you see, very small tiny grains are produced on the surface of the part. Reason, they solidify instantly. As we move inward from the surface of the part, we see a different microstructure. There are very small tiny tiny grains on the surface, and after a certain distance away from the surface, some different shapes of grains are produced. Indeed, they are long grains moving from the surface, from the external surface inward. This structure is called, this type of growth of the grain is called dendritic growth. Dendritic. And why does it happen like that? Because the first grain, which has been solidified somewhere, say for example here, it grows inward. Reason, the hot region is inside at the core of the material, which is here. And as the first part of the grain, part of the grain has solidified, it grows along the direction which is still at a higher temperature. Meaning that those atoms which are sitting here, the temperature of them is actually bent up, and eventually they do arrange themselves in the crystal structure which has started from the external surface. And the growth direction is inward. And from here as well, you can see it's inward. And this is the hot region inside. So what we get inside the material is not a unique microstructure. On the surface, we will have a different microstructure compared to the core of the material. Yet, we are dealing with a pure metal. What does this mean? Still, we have got the same same crystalline structure inside the material and same composition, because it's the same material. It's a pure material. Okay? Now, let's compare it with a case when we are dealing with an alloy. When we have two components in the molten material, say for example, copper and nickel or something else. What type of microstructure do we expect to see in an alloy when it solidifies? You know, the melting point of the two is not the same, it's different. Does it have an impact on what we get? Yes or no?
Yes.
It should, yes. And this is what we get for an alloy, which is very different to a pure metal. As you see, the skin of the material is still the same. And again, we've got dendritic growth of the grains inside the material. However, at the core of the material, again, we have got small grains of the material. What explains this structure?
Different metals have different cooling rates.
Say that again, please.
Different metals have different cooling rates.
Different components have got different freezing point or melting point, which explains this. Meaning that those at the surface will be richer in one component, those grains inside the material will be richer in the other one. Got that? The one which has got a higher melting point, sits on the surface because the temperature is going down from the top. So those atoms which tend to solidify first are the ones which have got a higher melting point. The other ones still move away because it's not the temperature for them to freeze. Where are they trapped, the other atoms? At the core, where it is the hottest point. Okay? So what we get is that the surface, some small grains on the surface, which is component A, for example, with a higher melting point, and those sitting at the core, in the core are the ones which are richer in the other component. And the melting point is lower, of course. And that's the last point, position or section of the material to solidify. Right? How about those grains which are long and also they actually are solidified by dendritic growth? What is the composition of those grains? Well, something between the two. Something between the two, right? Meaning that, do you recall the segregation which I explained in the casting process in a few lectures back? The segregation process, when we have got a grain which is at the core is richer in one component, on the surface it is richer in the other. Remember that from lecture 2, I assume? Yeah? Those grains have got actually those grains in here are segregated, meaning that in the core they are rich in one, on the surface they are rich in the other one. Now, are these richer? Let's talk about the core of this particular grain. In the core of this grain, do we see more component of this or that? Which one? In the core of this grain, is the material richer in atoms of this or richer in the atom of that one? External one, right. Because it's the first point which solidifies. And eventually, as temperature drops more and more, atoms of the temperature is closer to the freezing point of these ones. So as we move away from the core of the surface, the composition is closer to the composition of this. In the core, the composition is closer to the, to the composition of those grains on the surface. Indeed, in alloy solidification, we have got a macro, say two types of segregation. One of them is in the shape of the grains. The other one is in the composition. Now, let me ask you a question. Is this composition a desirable composition? Or this microstructure, is it a desirable microstructure and composition that we have achieved? It depends on the application. What happens if I subject this given component to temperature and to elevate the temperature and raise the temperature from room temperature to whatever? Just keep going up and up. What happens after some time? When the melting point of the first component has reached, but the melting point of the second is not yet reached, what happens? Material will disintegrate. Meaning that those grains, say the melting point, let's talk about these grains. Let's talk about these grains first. These grains. In the core, we have got component A with a higher melting point. On the surface, we've got component B with a lower melting point. So what happens is that the surface of the grains will be melted while the core is still solid. As a consequence, those grains get disintegrated from one another. And what you get is a disintegrated material or part, which is not desirable. How can we deal with this problem? How can we improve the properties of the material? We had that before. Heat treatment. Put the part in the furnace at elevated temperature, leave it for some time. When you are putting it in the furnace, you are increasing the rate of diffusion. And then atoms of components B and A can travel long distances inside the material. And after some time, what you get is a unique composition or distribution of atoms inside the material and unique properties, making the component all the same. And you achieve unique properties. If you don't do that, inside of the material, you've got one component, on the surface, you've got different component. So it's not a desirable alloy which you have produced. Okay? Does it make sense?
It's stress relief, right? It's stress relief.
The stress also will be relieved in the heat treatment process. If it's subjected to heat treatment process, also it acts as a stress reliever as well.
Welding, it's, it changes steel, so when you put the heat,
Mm-hmm.
you press like tension down, you have to
Yeah, always, there is residual stress left in the material when it is subjected to heat treatment or hard working. If you want to get rid of that, put the material in the furnace, elevate temperature, and leave it for some time. It does act as stress reliever and elongates the lifetime of the part. Okay? There is an important equation in this slide here, total solidification time, TTS, which is defined as a function of V, which is the volume of the cavity, and A, its surface area. This is an important, very important equation in the casting process. Okay? Very important. Reason, when you can compute the solidification time which for a given part, then you can also compute solidification time for the riser. Right? We want to design the die in a way that riser solidifies after the cavity or after the part. If we can compute solidification time by making use of this equation for the cavity and also solidification time for the riser, then we can design it in a way that riser always solidifies after the part or cavity. So this is an important equation. Or sometimes we have got a number of parts. This is very important. Sometimes we have got a part which has got different sections, or we want to produce a number of parts in a single mold. We've got to arrange them in a way that the one which is at a larger distance from the riser solidifies first, and the one which is closer to the riser solidifies last, but still before the riser itself. How can we make that happen? By making use of this equation. It's the equation which is telling us which cavity solidifies first and how much time is needed to solidify each of the cavities, so that we can put them in the right order. Okay? What we have got in this equation, as I said, V is the area of the part or cavity or whatever it is volume, A is area, N is an exponent which is often 2, depends on say some characteristics of the casting process. In our problems we always substitute 2 for N. So it's simple. And Cm is the mole constant, which depends on some characteristics of the molten material and also the die cavity. We've got to work this out, or it should be given to us in the statement of the problem. Okay? Now, let's skip these ones. I'm going to actually ask you to do this problem. Okay? That's an application of this given problem. Let's see if we can. This is an important problem and more similar to the ones that you are expected to see in the exam. Answer to your question. Okay? This is more similar to the ones that we are supposed to see in the exam. Let's see if we can do it ourselves. Well, the equation is given to you. You know N is 2, V you've got to compute it, A you've got to compute, Cm you've got to find it, TTS is given. This is an interesting problem, you see. Okay? So, spend some time doing this problem. You may work with your partner if you want to. Maybe it should be done also. Cm is not given, but you can compute it yourself, okay? by making use of the information which is given, we should be able to compute the value of Ca and then make use of it for the problem. Are we making any progress with the problem? Yeah? Why are we interested in solidification time TTS for riser which is greater than that of cavity? Because it should always be the case. Always the solidification time for the riser should be greater than that of the cavity. And what type of geometrical shape makes this possible? Well, which shape makes it possible or more desirable to increase the solidification time as much as possible? A shape where we have got a higher V over A ratio. And which geometry has got that one compared to other ones? Which geometry has got a higher V over A ratio? Spherical shape first, followed by cylindrical shape. And that's one of the reasons that risers are always made in cylindrical shapes, because we want to lower the area as much as possible and lower the V over A ratio. Okay, making a spherical shape is more difficult, so often we make use of cylindrical shape. But spherical shape is still fine. Okay? And we've got to do this computation for the cavity and for the riser always to be sure that TTS for cavity for riser is greater than that of the part itself. Okay? And if we have a number of parts, then as I said, the one at the larger distance from the riser should be the one which solidifies first and it has got the lowest TTS. And then we move the other way. As TTS increases, part is closer and closer to the riser. And of course, TTS for riser should always be the greatest in a mole. Okay? Are we done with this problem? First, we've got to compute the value of Cm. On the basis of the information given, we should be able to. Right? Because TTS for the part is given. And then we can compute V and A because dimensions of the part are also given, right? Having this information at hand, we can compute the value of Cm, which is 3.26 units per square centimeter. Okay? Should be cubic centimeter. Should be cubic. Anyway, that's the value of Cm. Once we have this at hand, what is left to be done? We are not provided with the information of area and volume of the riser. What we are given is what? Is only the ratio of diameter to height, which is 1. Okay? Having this at hand, we can write the equation for volume of the cylinder and the equation for the surface area. Like that. And we know D and H are equal. Can we substitute one for another one? Of course we can. Having this done, we achieve a V over A ratio which is equal to this. D divided by 6 or H divided by 6, it's the same. Okay? Then what is left is to substitute this ratio in the say solidification time equation. Instead of V over A, we can substitute this value, and the only unknown value is this parameter. Because we know TTS should be equal to 2, and the only unknown value is this. Easily we can compute the value of D, which is also equal to H. Okay? It's as simple as that. This is similar something that you might see in the exam. Okay?
Exactly.
Not exactly this one. Similar to, I said. Okay, similar to, something like this. You need to play a little bit with equations to get the answer. Okay? But anyway, it won't be hard, believe me. If you are prepared, if you are done with the problem, you shouldn't find fun to do the problem. You shouldn't. Okay? Now I'm going to play a video clip on the casting process, which I think is of interest, should be of interest to you. Just an explanation of what we have discussed in this lecture so far. Okay.
Sand mold casting, also called sand casting, is the most common casting process. It is applicable to a great variety of metals, and there is essentially no limit to the size of casting that can be made. Castings made in sand molds are not very precise, but production cost is generally lowest. Although the molds are expendable, the sand can usually be reconditioned for reuse. Sand molds, made in halves, are built by tightly packing the sand around the pattern in a flask. The upper mold half is called the coat, and the lower half, the drag. The mold includes one or more risers, venting provisions, and a system for transferring the molten metal to the mold cavity. This system includes a pouring basin, sprue, runner system, and one or more gates. Once the sand has been compacted, the pattern and mold half are separated, and any loose sand is blown away. Cores, if required, are inserted into the mold. Once they are set, the mold is closed by aligning the coat and drag. The mold is then transferred to the pouring station. In casting, metal flows from the pouring basin through the sprue, runners, and gates to the mold cavity. Vent holes formed in the coat and drag, and often in the cores, permit trapped gases to escape. After filling the mold, the metal enters the riser or risers, which serve as reservoirs of excess metal to compensate for metal shrinkage during solidification. Once cooled, the casting is removed from the mold, and the metal in the runners and risers separated from the casting for remelting. Casting in sand molds is classified based on the type of sand used and variations in the mold-making process. These variations include casting in green sand molds, no-bake molds, and in shell molds. Green sand molds are made from a flexible mixture of silica sand, clay, and water. The sand is said to be green because of its moisture content. Although casting in green sand molds is a versatile process, thin sections are difficult to cast because they may be eroded by the molten metal, or the metal may cool and become solid before filling the sections. Also, part tolerances and machining allowances must be rather liberal. Very smooth finishes are not attainable, and certain metals can develop defects if cast in molds that contain moisture. Investment casting is a precision process using primarily ceramic shell molds. Investment casting is also known as the lost wax process because wax, a principal pattern material, is consumed during the mold-making process. Consumable plastic patterns are also used. Investment casting patterns are made by injection molding. These patterns are assembled onto a wax post connected to a pouring cup. This pattern assembly, called a tree, usually incorporates complex runner systems to assist metal flow in the investment casting process. The shell mold is produced by dipping the pattern assembly several times in slurry and allowing it to dry between dips. The first slurry mixture consists of fine particles for smoothness. Subsequent dips are mixed with coarse particles to quickly build up thickness and provide strength. The wax is removed from the mold by melt-out in a furnace or autoclave. Then the mold is fired to remove moisture, cure the ceramic, and to preheat it for pouring. Both ferrous and non-ferrous metals can be investment cast. Once the metal has solidified, the mold is broken and the casting removed. The main advantage of investment casting is the complexity of shapes that can be cast to close tolerances, thin walls, and smooth finishes. Most investment cast parts weigh less than 4.5 kilograms. However, parts weighing over 100 kilograms are also made. Evaporative foam casting refers to the use of expendable polystyrene foam patterns in molds made of dry, unbonded sand. The process is also known as the lost foam or expanded polystyrene process. The pattern may be a single piece, or for complex shapes, an assembly of molded pieces. Patterns also can be clustered in groups to produce multiple parts at a time. The pattern is coated with a thin, high heat-resistant coating, usually silica. Once the coating is dry, The pattern is placed in a flask and surrounded by sand, which is vibrated for compaction against the pattern. Casting then proceeds with the poured metal, evaporating the polystyrene foam and filling the cavity formed by the pattern.
Okay. Any questions on the video clip that we had?